All right, in this lesson, we are going to look at finding the total area between two curves. And if you want to print a sheet to kind of follow along, this is a sheet that I kind of use for the problems and examples that I'm going to give you in this lesson. So let's look at finding total area contained by one curve or more than one. And this is just your old-fashioned find the area under a curve, which really means find the area between the curve and the x-axis. And this should be nothing new. If you want to measure the area between a curve and the x-axis, it is simply the antiderivative from a to b of your function times the x. And so that's old stuff. That's just area between the curve and the x-axis. Now, one thing to mention in these areas, we will always give answers that are positive. We are actually finding the area. Now, I know there are instances where indefinite integrals produce a negative answer, but that depends on the context of the problem, whether you keep the negative or if you want to get rid of the negative. And in these answers, we will always have a positive answer for the area between the curves. And in this case, if you want to say between curves, you could say this is between the curve. Y equals f of x, and the x-axis is the line y equals 0, if you want to think of it as those two curves. But anyway, I talked too much. Onward we go. Let's look at this one. And again, we're doing the area just between the curve and the x-axis. However, if I do the antiderivative from a to b of just f of x, well, that actually will produce something negative. That's going to be some negative answer, and I want these answers to be positive. So we have two ways to make this positive. And we could, I'm going to call this A for the area of that region, we could simply put a negative in front of that antiderivative, and now that will return a positive answer. Or if you remember your properties of integrals, we could do the integral from B to A and make that a positive antiderivative of f of x dx, and that will produce the positive area, that is the area that we are looking at in this gray region here for number 2. Now it starts to get a little bit interesting when I bring two equations, two functions into the problem, and I now want the area of this gray region between the graphs of f and g. And this is the easiest one for people to visualize, and a lot of you are probably already figuring it out, but I'm going to kind of walk through it with my friend Triangle Man here. And sometimes it's a little bit easier to process problems if you can kind of just think, well, what if I had a number for the area under f and a number for the overall area under g? And so that's what my Triangle Man over here is doing. He's thinking, I suppose the area from a to b of f of x is, and we're going to give that a number, just something to play around. Let's say that that area is 10. So all of this from f of x all the way back to the x-axis is 10. And then the area under g of x, well, the area from g of x to the x-axis is considerably less than that. I'm just going to say maybe 4, right? Well, if the area under f is 10 and the area under g is 4, we really need to get rid of all of this area under g. And so the total area between the two will be 6, and you'll get that by subtracting those two. And so the setup for this one is going to be the antiderivative from a to b of my f of x. That's going to give me 10 minus, and then I'll take away from that the area from a to b of g of x. Now, in these problems, the overwhelming majority of the time, the limits of integration, kind of stumbled over that, the limits of integration will be the same, and if they are, you can combine that into a single antiderivative, which is what we typically will do, and make it a single antiderivative of f of x minus g of x. And then just to make sure you don't anger the gods, you should have that difference, f of x minus g of x, in parentheses, because you want to multiply that whole difference by the dx. But again, you're typically not counted off of that if you are in AP Calculus on the AP exam. If you're in college or if you have another teacher, you'll just have to ask your teacher how strict they're going to be with that kind of notation. Okay, so let's look at this one, number 4. Very similar situation, and it's really the same situation we had before, only this time the intersections of the two curves. The curves are actually intersecting, and those are creating the bounded region between the two, but it's still the integral from a to b. And I don't really need to suppose much of this one. F of x, just be careful, f of x this time is the one on bottom. So if I want to say that area under f of x is, I'll give you a number, let's call that 7. Then the area under g of x, which is the top one, the area under g of x is going to be more than that. That could be something like 11. And then if you subtracted those, that would be a net area of 4 between them. But I'm not going to bother writing it out. Well, I just guess I just did. But I could do the area under g, because g is the one that's above the f function, so a to b of g of x. And I guess I'll do this separate, dx. And then we will take away from that the area from A to B under f of x. And there's really no difference between this example and the first one other than the g of x is on top and the f of x on bottom, and their intersections are creating the limits of integration. There are many times, let me finish this before I go back, A to B, we can combine that into g of x minus f of x dx. Only one dx. Many times the curves don't actually intersect, and they'll give you like vertical lines to be your left and right boundaries to contain the region. Sometimes they don't do that. Sometimes the curves themselves contain the region. That's what happens on 4. And then it starts to get a little bit different when we have like one function above the x-axis and one function below the x-axis. And here is where, if I just let my students kind of guess and try to figure it out, I hear a whole bunch of different things. I'll hear things like, ooh, we need to do f of x plus the area of g of x, or g of x minus f, right? I hear a whole bunch of different stuff. But again, let's just think about what happens if we consider those two integrals separately. The area under f, the area from a to b of f of x is this region. And if I wanted to suppose I had a number for that, I could call that maybe 4. Or you can call it 12 or a million if you want to. We're just kind of making stuff up to feel our way through the problem. The integral from a to b of g, well, that area, if this blue area is 4, this looks like a little bit less than that. I'm going to call that 3. I'll call it 2.5. However, because I cannot write today, 2.5, because that is below the x-axis, the definite integral of g would actually produce a negative area. So if the area under f is 4 and the area under g is 2.5, we need to add those areas, 4 plus 2.5, but since g is producing a negative answer, in order to add those two, we need to do the area of f, that's the 4. If I add to that the integral of g, which by the way, this is wrong, if I add to that, we actually end up doing 4 minus 2.5. We're going to subtract that. So that minus the negative, we end up adding that 2.5, and we end up getting 6.5. But of course, those are just kind of made up numbers to give us something that we can wrap our head around and process the problem. And once again, we can combine this into a single antiderivative, f of x minus g of x dx. And there is your setup for when one curve is above the x-axis and the other is below the x-axis. Cool? All right. Now, what if they're both below the x-axis? Well, let's play the what-if game again. Let's think with Triangle Man here. Suppose the integral from a to b of f of x is, and that would be all of this, and this is below the x-axis, so this integral will produce a negative value. I'm going to call that negative 6. And if that's the case, then the integral from a to b of g, which is this green region, that is also going to be negative, but the magnitude of that area is less than that contained by f, so I'll call that negative 2. And so if it's negative 6 and negative 2, that's going to be an area of 4 between them. I can kind of play around with the numbers there, but we can get that positive 4 area between them by doing the antiderivative, and we'll actually start with g, negative 2, and we will subtract that area of f. And those are from a to b. The limits of integration are part of the setup, which once again, we can combine that into a single, nice, clean antiderivative of g of x minus f of x dx. And there is your setup for when both curves are below the x-axis. Now, you may be thinking this is a lot to have to remember, because, okay, we had one setup for above the x-axis, and we had to think differently for when one was above and one was below. Now we have both of them below the x-axis. But if you are paying attention to the setups for these, I'm going to get rid of all that. If you pay attention to the setups for all these, you may notice an overarching theme for the last 4. Whenever we had a curve on top and a curve on bottom, regardless of where they are in relation to the x-axis, my setup always ended up being my top curve. In this case, it was f of x minus the bottom curve, g of x. So the antiderivative of top minus bottom. Look at number 4. It was the same thing. If you follow that g of x is on top, f is on bottom, top minus bottom. Number 5. They were split by the x-axis, but it doesn't matter. Top curve minus bottom curve. Number 6. They were both below the x-axis, but it didn't matter. When I did top curve minus bottom curve, it kind of took care of all those crazy negatives that you may be struggling to wrap your head around. top minus bottom. And so, and I didn't put a blank in here on your notes sheet for this, but the takeaway from those first few is when you are finding the area between two curves who are functions of x, and we are going to be getting into functions of y this unit. But if it's functions of x, you will always do the integral from a to b, and I should have said that in these setups, a is less than b. You do the integral from a to b of your top curve minus your bottom curve dx. And then we can either do that by hand if it's fairly clean. You'll very frequently, especially in AP Calculus, get really ugly antiderivatives where you are expected to simply put them into a calculator. Okay. So now what if we do have functions of y? Now this is a little bit different, and this is going to be one of the things we struggle with in this unit, is we will have several situations where we are dealing with functions of y, and I'm just going to go ahead and tell you that when it is a function of y, we'll do the integral from a to b. So we work up the y-axis when we evaluate the integral. And it's always going to be your right curve, g of y, minus your left curve, which in this case my right is g of y, my left is f of y, dy. And you can do that in separate antiderivatives if you want, but it's always going to be right curve minus left curve. Number 7. Oh, never mind, there's that some overall takeaway for that. It's always going to be right minus left if it is a function, if it is two functions of y. Two functions of y. And here I did mention that a is less than b, and there is always found by doing the antiderivative from a to b of right minus left. Then number 7, and again, just like with the x's, it does not matter where the two curves are in relation to the y-axis. That area is going to be my right curve, which now is f of y, minus my left curve, which is g of y. I'm going to make sure I wrap all that in parentheses, multiplied by dy, and then we are going from y equals a to y equals b, and then we have to figure out how we're going to compute that antiderivative to evaluate to get the area. Okay, last one. Here we have two curves, except they intersect more than once, and so if you pay attention here, you'll notice if we follow the f of x, f of x is on bottom between b and c, but on top between a and b. So we have two ways we can do this, and the way I typically will do these is I will do the area from a to b, because on that region, my top curve is the f of x, bottom curve is g of x, and then I will add to that. Now, if I go from b to c, my top curve has changed, so now I'm going to do g of x minus f of x. And that is the way I typically do this, because these are very frequently non-calculator questions, and I think that's the easier way without a calculator. If it is a calculator question, you can actually do this quickly in one antiderivative. And I'm going to explain this with my students in more detail later. I'm not going to give a thorough explanation in this video, but I will just tell you that if you do the absolute value of their difference, you can actually, that should have been from A to C, you can actually go from A all the way to C and knock all of that out in one antiderivative, and that will work. And I suppose I could have, looking back at some of these, I suppose I could have used some absolute values with these, like number 2. I could have just done the antiderivative and done the absolute value of f of x. However, these are, like I said, very frequently non-calculator questions, and dealing with absolute values without a calculator can be a little bit tricky. So I kind of default to not using absolute values to rectify any negatives. Wow, that was a really big thought cloud. But, like I said, if you have multiple areas created by multiple intersection points, like we had on number 8, you can use absolute values. So there are the generic notes, and I have 3 examples to look at on how we can find the areas between graphs. And one thing that will come in handy with this unit is being able to graph curves relatively accurately. It does not have to be beautiful and wonderful, but you have to be able to graph well enough so that you know which curve is on top and which curve is on bottom, or which curve is on the right and which curve is on the left. And so these I'm going to graph very quickly. It's y equals x squared plus 5, which is x squared shifted up 5. It's going to look something like this. Wow, that was nice. There's y equals x squared plus 5. Oh, that was horrible. And then y equals x cubed comes up through the origin, and then I need to start at x equals 0. So here's x equals 0, and x equals 2. And if I plug 2 into both of these functions, 2 squared plus 5 is 9, and 2 cubed is 8. And the reason I did that is because I know that these curves will eventually intersect, and I wanted to know where that 2 is in relation to that intersection. But since the parabola has a higher y coordinate, I know that 2 happens before that intersection, and that is absolutely horrible graphing. But I'm kind of glad I did that, just to reiterate the fact your graphs don't have to be nice. There's our region, and for the setup, it's going to be the antiderivative of, and here we have a top and bottom situation, so x squared plus 5 minus my lower curve, which is y equals x cubed. We want to wrap all of that in parentheses times the dx, and then we'll evaluate that from 0 to 2, and there's your setup for number 1. Now, since the setup is the only thing new right now, I'm going to pause the video and work this out and just show you the answer in a couple of seconds. But you should absolutely be able to work through these antiderivatives and finish them on your own. If you want to practice that on your own, you can pause the video and see if you get the same answer I do, and that'll show up in about 3 seconds. Okay, I did that very quickly. I ended up with 26/3. Now, just a reminder, in AP Calculus on the AP exam, this is a fair stopping point where you have all numbers, but if this is a multiple choice question, you obviously need to simplify. So I say go ahead and simplify just for the practice, because you will definitely have things like this on the multiple choice portion where you'll need to clean that up. And hopefully that's right. If it's wrong, let me know. Let's look at number 2. The area enclosed by these two graphs. Now this one's a little bit different than the last one because the first one we did, we had 2 curves given, but then they gave us the x's right here that served as the left and right boundaries, which were the limits of integration. We are missing that in number 2. We have a parabola that opens up, and we have a line. And so we know, since they didn't give me anything else, that these two graphs completely by themselves must enclose a region. And so I'm looking at the shapes of these graphs, and this is where, like I said, your graphs don't have to be perfect. I have a parabola that opens up, and I have a line with a slope 3 and a y-intercept of 4. That's going to look something like this. The only possible way those two graphs can enclose a region is if your parabola is like this. That's terrible. And if your line comes through it like that. That's the only way we can enclose a region with these two graphs all by themselves. And with that, I already know that my top curve must be the 3x plus 4, so the antiderivative of 3x plus 4 minus the antiderivative of, well, minus x squared. I'm not going to do a second antiderivative. And there is our integrand. Now we need the limits of integration. Since they did not give us the limits of integration, we need to find the intersection of these two curves to serve as the limits of integration. So we're going to do that, and that's going to require some algebra 1, and since you are in calculus, I will assume you can find the intersections, and I'm going to do that with the video paused. Okay, I got -1 and 4 for my limits of integration, and if you trust your algebra, that's great. I don't have a graph that can confirm that, so it might be good to try to have a relatively accurate graph, because if you have a relatively accurate graph, you can know if your intersections make some sense. And so that's what I've done behind this little box, is I decided I'm going to take just a few seconds to graph this a little bit more accurately. These two graphs are very easy to graph, or they should be anyway. I have a parabola at the origin, then the line 3x plus 4. That's probably not truly a slope of 3, but I can tell with this more accurate graph, I will have one intersection right over here just left of the y-axis, another one over here a little bit further away from the y-axis, and that's consistent with -1 and 4, so I feel good about my answers. But like I said, if you trust your algebra, you don't need to worry about the accurate graph. It just gives you a little bit of a better feeling about what the actual intersections are. And then, like before, I'm going to pause the video and work out this antiderivative and show you the actual answer in a few seconds. All right, here's my wrong answer, and I thought about erasing it or fixing my mistake, but I wanted to show you just something that's good about these problems. You know you're going to get a positive answer. You will always get a positive answer with these, and I got a negative answer, and so I got to this point, I was like, what the heck's going on? And then I realized, oh, my minuses right here magically turned into positives, so I'm going to fix that. Just something to keep in mind with these problems. You know you're going to get a positive answer, so a little bit of a safe check for me right there, and I'm going to fix that and come right back to the last problem. Okay, that took me entirely too long. Turned out that was not where my mistake was. My mistake was somewhere else, but I ended up fixing it, after forever, and I ended up getting 125 over 6, and I hope this is not a multiple choice question because those fractions were brutal. Okay, last one. I'm going to do this one kind of quickly because I'm already at 20 minutes and I don't like my videos getting this long, so my apologies. So I'm looking at x equals y squared and x equals y cubed, and I need to know the region between those two, and these are functions of y, which is where we are going to be a little bit less comfortable. So x equals y squared, we should know is a parabola opening to the right, so I'm going to rotate that. And x equals y cubed is the same thing as y equals the cube root of x, which is actually going to come up through the origin like this, and the way these are going to intersect and have a very tiny sliver of area is going to do something like that, leaving this tiny area right here. And I could do top minus bottom on this one, but I'm going to do right minus left because the functions are already in terms of y, and I can look at that region, and my right curve is the parabola, y squared. My left curve is the y cubed graph, that's dy. And then as far as intersections, sometimes you can just kind of look and guess, and this is one of them. They clearly intersect at the origin, and then you can just look at it and tell that one squared and one cubed are the same, so the upper limit is 1. So there's your setup for this one. It's a right minus left, like that. If you mess up your graph and you accidentally did left minus right and everything else was good, then you would end up, or if you got those functions backward, you'll get the right number, you'll just get the negative of the right answer. So like before, I'm going to pause this and work it out very quickly and show you the answer, and then I'm going to quickly end the recording because it's way too long. There you go. 1/3 minus 1/4. If it's a free response question, just leave it there. Multiple choice cleans up to 1/12, and I'm done. Sorry this got so long. Bye-bye.